Okay, so I'm back with my area of expertise, actually, which is microgravity combustion science. And I'm David Urban again, and like Brian, my branch manages the Microgravity Combustion Research Program that's conducted both currently on the space station and previously on the shuttle. And we also do work pertinent to exploration, in particular looking at spacecraft fire safety is our main area of the applicability of reacting systems to exploration, but we also do work in, for example, in situ resource utilization, where you're reacting, in most cases, soil to produce useful materials. And these are just a bunch of collage of pictures from various things, but some of these expose the fire safety issues. This is smoke, particularly from space craft materials. This is a burning droplet. So this is one of the big reasons people like to do combustion research in low gravity is it gives you access to one-dimensional systems. And so it's perfectly spherical. Flames are possible, and it makes a lot of the study a lot easier. Things change a lot. This is a 1G flame of spreading across a liquid, and this shows you the 0G one. Very different. You don't have the buoyant flow lifting up the flame up. I'll discuss this in more detail, but next slide, please. So first off, the question is why does NASA care about combustion? And despite all the progress we've made in energy, et cetera, our primary energy source is still from combustion. Roughly 85% of the delivered energy that you use every day comes from a combustion system of one kind or another. It's a primary cause of global warming and of air pollution, and affects people directly every day. It's also an inherent part of many industrial processes. They're really glass making, steel manufacture, et cetera, count on there being a combustion process. You couldn't do it the same way with an electric system, for example. It's also a major source of the loss of property and life, and both in building fires and in wildfires. It's the power source for portable applications, cars, trucks, trains, and it's a catastrophic hazard for the manned space flight program. Also, many new materials. We're looking at nanotubes, diamonds, ceramics, et cetera, are made in combustion reacting systems. And so it's really gives you a chance to make a carefully controlled environment of high temperature synthesis conditions. And people often argue that it's man's first technology, but it's also one of our most complex and still incompletely understood. Next slide, please. So, on that note, I think the biggest challenge to the discipline is everybody goes, "Oh, fire, we understand that. I've made fires as a kid," and it's been so pervasive in human life for so long that people think it's well understood. But the reality is that substantial improvements in the quality of life in space or here on Earth will require substantial improvements in our ability to predict and control combustion. And that's a wildfire picture. This just shows, I don't have the companion photo, but this is the soot coming out of a earlier generation aircraft. And that's soot control is one of the major problems we have with air pollution. The small particles you get out of combustors are in the very hazardous range. The PM 2.5 type particles are a big concern. And this is a recreation of the Mir fire we did on ground base. So that's an estimate of what it was like. Unfortunately, they were a little too busy at the time to take pictures. But this is actually the hardware that came back from Mir and showing you the dramatic destruction of the oxygen generator. So it's a real concern for manned spaceflight. Next slide, please. So the things I'm going to try to cover are what areas can microgravity research contribute to the field of combustion, and what progress have we made, and is there room for more progress, and also what can microgravity combustion tell us about and contribute to exploration goals. Next slide, please. So there's a lot of detail within the general concept of fire, and so there's, without spending too much trouble, people that talk about combustion worry about is it premixed or not premixed. That's whether you're, for example, a gasoline spark injection engine is premixed, your diesel engine is not premixed. Is it a spray like in a jet engine, or in diesel? And are we talking about particle cloud fires, like in coal mines and grain elevators? Or are you talking just flame spread across the surface as in a building fire, or smoldering, which is the initiation source of many fires? And also, finally, are you trying to synthesize something with a reaction system? And the reason why we'd like to study this in low gravity is that within a flame, the temperatures rise from room temperature to as much as 2,000 degrees centigrade, and that causes a huge difference in the density, and so you have huge buoyancy-driven flows, which dramatically overwhelm many of the other things occurring within the flame. And you have settling and stratification of components. And the other reason is you can get a one-dimensional spherical flame, such as I mentioned, which makes numerical modeling much easier. And then you can also stretch the flame space in ways that make it much easier to model. And so it gives you better opportunities to make detailed measurements of what's going on. And the applications of all this are things like explosion control. Big one economically is increased efficiency and reduced pollution. But for spacecraft, we've got the big reduced fire risk for the spacecraft. And finally, new materials and nanoproducts, which are one of the new areas of industrial production these days. Next slide, please. So what have we seen out of it so far? And there's some examples of how the work to date has already appeared in a number of textbooks. These are all sort of fundamental combustion textbooks. There's also a recent book on safety design for space systems, has a big section on spacecraft fire safety, incorporating the latest results. And recommend any of these if you want to look at what, this is a nice overview of all of the aspects of combustion, microgravity combustion, fire and free fall. But there's also this book if you want to focus on spacecraft fire safety. This is the example that is most prevalent in the media. Gives a good example for the layperson of what they were talking about. This is a 1G flame, and this is a candle flame picture taken up on mirror. And as you see, with there's no preferred direction. The flame assumes a shape more or less like a hemisphere. And the other thing that's significant is that there's dramatic reduction in the brightness of the flame, which means there's very little soot, which is what makes flames bright in this low gravity flame. And so this has been very neat because it's a very good cogent example, and it's in a lot of educational materials in school publications. It's really taken a life of its own, two simple photographs. Next slide, please. So what do we care about in flame spread? The interesting thing is, a fire makes its own flow in 1G. So if you have a flame, the hot gas, as I mentioned, rises rapidly and gives you a minimum velocity below which you can't go, whereas in spacecraft, you don't have buoyancy, and the only airflow you have is whatever the ventilation system provides. And that's lower than the airflow you get from the flame itself. So you have conditions of very low airflow that exist where you can have a flame in low gravity. And it turns out those are conditions of increased flammability compared to 1G. The airflow caused by the buoyancy supports the flame, but it also blows it out. And so the answer is that we have a condition, this is oxygen concentration, this is air velocity. This brown region is where it's flammable, and this is the minimum air velocity you'll get in 1G. You'll see there's this lower velocity region where you can have a fire, sustain a fire in low G. And so we also see a similar non-monotonic dependence on gravity level. So it turns out the most flammable conditions are somewhere between the lunar and Martian gravity level. And so, which again is more flammable than here on Earth because you don't have the airflow blowing it out. Another issues that are of concern is the actual ignitability of material can increase at reduced pressure. The burning rate doesn't necessarily increase, but the things are more easy to ignite. So the prevalent assumption that 1G is always the worst case for fire safety is not really maybe incorrect. And so there's a whole lot of work, development of a predictive understanding of ignition and flame spread, particularly for thick fuels, is quite incomplete. Next slide. So an example that's most, for flame spread is if you ignite a piece of material in the middle in 1G and blow across it, the flame always goes downwind. And so if forest fires, everything always spreads downwind. In low gravity, again, if you can have conditions of lower airflow, and in fact, this spreads quite the opposite, and they'll spread upwind because it's seeking oxygen. And the reduced airflows you have in low gravity, so you have this, the wind is coming, in this case, coming this way. This is the leading edge of the flame, and there's an oxygen shadow behind it, and it's actually pursuing upwind. And so it's quite contrary, again, to normal gravity experience. And likewise, at very low limiting airflows, we have this bizarre spider-shaped flame spread, where, again, it's seeking oxygen boundaries. Next slide, please. So in the very fundamental area, looking at premix systems where you mix the oxidizer and the fuel, and then you try to ignite it. Again, the example in your life is your car engine. But if you go to very low energy conditions, a Russian mathematician, Zadovich, whose name is throughout the combustion literature, but he also was one of the fathers of their atom bomb, over half a century ago predicted you could get these steady flame ball structures where the right conditions of the conductivity and diffusivity of the gas, the flame would not grow. It would just be supported by diffusion of products back in. But no one could ever test it because of the buoyant gravitational effects. But shuttle experiments demonstrated indeed this was the kind of flame structure was possible and could persist for tens of minutes without moving. But likewise, we've also looked at other structures, including cool flames, and so you can also establish gradients of reactivity where you have different concentrations across the mixture, which wouldn't be possible in 1G due to buoyancy. So this gives you big opportunities for real fundamental studies, and looking at, again, flame propagation through gradients of reactivity, cool flames, which are a particular case of flame before the normal ignition you think of. They're still quite hot, but they're cooler, only a few hundred degrees C, which is it's the sort of initial phase of ignition. And it's of interest in, for example, aircraft engine tank fires. Is the ignition phase is going to be a cool flame. And then other limiting behavior. Next slide, please. So looking at non-premix systems like a Bic lighter type flame, the buoyancy intrudes on the flame structure even at high Froude numbers, and so which would be high velocities. So simple flame-shaped models have been validated by ground-based microgravity testing, providing classical data for textbooks. And a good example is even if you're cranking, this is Reynolds number, even if you go into the turbulent regime where you think your velocity is so high, how can gravity matter? It turns out that the low-gravity flame boundary is way up here compared to the 1G flame height. So there's a big difference even in systems where people would predict that the velocities are high enough gravity shouldn't matter. So it gives you a real opportunity for ideal flames geometries for flame structure measurements. Next slide. Another area of very big importance is metal combustion, and it was a very surprising result. There hasn't been much research of this type up in space, but it's an important area because high oxygen systems, they have a lot of compressed oxygen up on spacecraft to support the crew. And one of the standard materials used is copper-bearing alloys because they're found to be low flammability in 1G. But it turns out, whereas copper is considered the sort of the gold standard of non-flammability in oxygen systems, it is quite flammable in low gravity in high oxygen systems. And this is because the melted fuel behaves differently. It tends to drip away and to take energy out of the system in 1G, where it doesn't happen in low G. So. And reduced gravity enables steady melt layer and gas flow conditions you don't see in 1G. And it's an area that's really poorly understood and worthy of more work. Next slide. So again, the classic system, there's a candle flame, and this has been an excellent tutorial for the public. And the classic diffusion system, in 1G, the airflow comes up, the hot air rises up here, and it draws air in the bottom, supporting the flame, which gives that upward shape. In low G, the oxygen diffuses in and the chemical products diffuse out. And so that's why you get this nearly spherical shape. And the net result of that slower process means there's less soot, which is why the flame is less bright. But it demonstrated also, contrary to, there's another belief that in long-term flames couldn't exist in low gravity because they'd run out of oxygen. But it turns out actually it's quite not the case. If you have a reasonably flammable material, though they can support themselves by diffusion alone in an air environment. And so in fact, this particular test, the candle finally went out because it ran out of wax, not because there was any shortage of oxygen supply. So, didn't have a good measurement system in there, but that's going to be on the order of 1,000 C to get the blue colors. But given the simplicity of the system, these experiments, we didn't have a temperature sensor in there. That's something we would like to address in the near term, but we haven't had a chance to do it for that system. Next slide, please. I've been mentioning soot, and those that don't know about combustion don't necessarily care, but or don't understand why they should care. But soot is is physical particles of carbonaceous material that form in a flame, and it dominates the radiant heat from the flame and the light. And so if you're trying to control flames, you've really got to control the soot in the flame, both from a pollution standpoint and also for the heat load. It's why you feel warmth from your campfire and why you can read by a candle. Whereas your gas stove has no soot in it, which is why you couldn't read by that. And so this going to diffusion flames gives you longer resonance times. It gives you an opportunity to study the soot processes more completely and get a better understanding of the chemical kinetics, and also gives you large scales, which allow better measurements of the structure. Next slide, please. So, and I mentioned droplet combustion, and this shows it's maybe one of our more complex experiments, but it's really amazingly cool. You have two needles, you generate a droplet of fuel, and then the needles pull away symmetrically, and you get a free-floating droplet of fuel. And you can only do this in a spacecraft-type environment. We've got long-term quiescent low gravity. Then you can come in, and with igniters, ignite the flame, and then you have a burning droplet of fuel floating in space with no disturbances. And it doesn't always work. It sticks to the needle sometimes, but you got a very good success rate releasing these droplets. And then you can have a beautiful one-dimensional system. That's the droplet in there, and that's the flame boundary around it. And versus in 1G, where you'd have a teardrop flame, such as you expect. And this gives you a beautiful model for environment for testing your chemical kinetic models, which you use to predict the combustion. And the applications are very substantial because again, 85% of our energy comes from fossil fuels, and about 90% of the transportation sector is liquid fuels, of which a huge fraction of that is burned in liquid spray droplet configurations. So this gives you an idealized geometry to develop the fundamental data to predict this and provide the building blocks for detailed combustion engine modeling for systems like jet engines, which again are spray. Next slide. So the question was, is there significant potential for future progress in combustion science? And our experience was the research community was not idea limited. A broad range of topics were pursued, ranging from fundamental combustion theory, applied combustion topics, and exploration-related investigations. And it was really due to budget constraints that reduced the amount of research in this area. There's still many unexplored opportunities in these areas. Next slide. And this just breaks it down into one way to split it up. And again, I've talked about this. The gaseous flames are a lot of interesting things going on there. By premixed and non-premixed, we can get these triple flame structures, flame vortices, turbulent flame suppression, etc. Droplet sprays, particles, and dusts. It's very interesting both for single droplets, but also in low gravity you can create arrays of droplets and that you can stabilize and look at, whereas in 1G you couldn't create these systems. Likewise, you can create particle clouds to study particle cloud combustion. Quite a bit of interest in combustion synthesis, giving you an opportunity to make unique materials that are important for new industrial processes. And then, as I've mentioned, the spacecraft fire safety is a big area. I'll talk a little more about specific cases in there, but that's directly relevant to all future exploration is understanding the crew fire safety. And there are other miscellaneous areas looking at propellants and flames with cold boundaries and development of diagnostics for future experiments. Next slide. So terrestrial issues where microgravity combustion can have an impact. Again, I mentioned energy. If we truly understand these flames, it can help us build more high efficiency, low emission flames, which can operate closer to the flammability limits, which means we can control the emission better. And again, since this is 85% of our energy economy, small changes are very significant. One area we're looking at is changing the structure of the flame to to make it easier to sequester the CO2 coming out of the flames. Typically, you're going to go to high oxygen flames, and also reducing CO2 through use of flames that are high in hydrogen. Soot control is critically important, and in other areas, if we're talking about hydrogen-fueled cars, hydrogen safety is a huge problem. Operating in low gravity gives you a chance to create some of the stratified ignition scenarios you're worried about for hydrogen refueling stations. Next slide, please. So now the other question is, can microgravity research make a significant contribution to NASA's exploration goals? Next slide. So there's several areas affected by reacting systems. One is fire prevention, detection, and suppression. This ties into extravehicular activity. It turns out the big trade space for spacecraft design really pitted fire safety against EVA because, as we'll describe in a minute, this trade-off in the atmosphere preferences. We're also supporting in situ resource utilization, reactor systems to produce useful materials on other planets, and again, environmental monitoring and control, specifically sensor design and post-fire cleanup for the spacecraft. Next slide. And particular areas of the fire safety are atmosphere selection and material flammability. How do you select an atmosphere so you have enough materials to build your spacecraft will be safe? Detecting a fire in low gravity where you don't have the buoyant flow to move the smoke all to the ceiling where you can detect it easily, and how do you suppress a fire in low gravity? And this is really based on all this long history of ground-based and space-based fundamental research. We've also accumulated enough understanding to make substantial improvements in the very practical issues of spacecraft fire safety. Next slide, please. Now, when I mentioned the trade-off with EVA, this gives you an example of what is the atmosphere like on a spacecraft. Now, this is the cabin total pressure, ranging from vacuum to 1 atmosphere, and this is volume % oxygen from 0 to 100. And so the shuttle and the Mir and the space station all operate at basically sea level air. So 1 atmosphere, 21% oxygen. Whereas the early Apollo, Mercury, Gemini, Apollo was pure oxygen at about 5 psia. And then working back, Skylab was only about 70% oxygen and coming back. Now, turns out the human physiology to the first order cares most about the partial pressure of oxygen. So they have a curve, it's called the normoxic curve, which is a constant partial pressure curve. And so the interesting problem is that fires care most about concentration. So you can, and the actual absolute pressure is less important to a fire than the amount of nitrogen-oxygen ratio. So there really is a different response between the two. So what happens is, if you want to go EVA, you can get decompression sickness from the suit. So they tend to they pump up the oxygen concentration and reduce the amount of nitrogen. And so normally they operate at 30% oxygen to prepare for the shuttle and the space station. Now the problem is, if you're going to the moon or someplace, you want to be going EVAs rapidly. You don't want the crew to be getting decompression sickness. So the goal is, can we find an atmosphere we can tolerate from fire safety perspective that will reduce the risk of decompression sickness. And I guess if you go too high in oxygen, you can actually get in trouble with oxygen toxicity. If you go too far this way, away from that green line, you can go in conditions where it's hypoxic and the crew can't function as well. And so there's a general region where it's deemed unimpaired performance. This blue line is roughly 1 mile elevations, Denver-type oxygen partial pressure. And that was found to be sort of the limit they could participate in for long-term low-gravity human performance. Next slide. So after much discussion trading this, again, the trade space for the Constellation's vehicles was going to put us at an average of 30% oxygen, but really the upper limit was 34% oxygen at a reduced pressure. And this would provide for the spacesuit conditions, which is pure oxygen, about 3 to 4 pounds. You would have no decompression risk. But the concern was really, actually, we had relatively little knowledge about low gravity material flammability in these conditions of combined reduced pressure and increased oxygen. So, and that was, looking at it fairly quickly, did find indeed, as I mentioned, that contrary to some intuitive understanding, as you come down in lower total pressure, things become more ignitable, although the burning rate is somewhat reduced. But the increased oxygen concentration was very significant. And so it ended up that the data we had to date made it clear this is a fairly safe condition, but we really need to get a complete understanding and be more careful about our material selection if we're going to be continuing to operate in these enhanced oxygen conditions. Next slide. So, as I said, it's a new condition. We have very limited material data in those conditions because none of the U.S. spacecraft were operating in those conditions, and pressure effects had gotten limited study. So the big question is, do the flammability limits change, and do the ones system NASA uses to measure this, is it really represent the low G behavior? And that's the big problem, because all the materials that NASA picks are tested in 1G. And so, and there's really not been an extensive test to verify that NASA's test methodology is really the best choice for approving materials for low gravity. And some things were completely not examined, actually, with, for example, flammability human hair, which turned out to be sort of surprising when we took a quick look at it. Next slide. So given the, and further areas are, given the increased flammability challenges imposed by the new spacecraft atmospheres, early detection is of increased importance. And until very recently, virtually no work has been conducted looking at detail at the detection of fires in low gravity, whereas right now we're doing a test looking at, on the space station at this moment, looking at the changes in the particle size distribution for if you're trying to detect a fire from the smoke particles. But there's really not enough understanding of how you'd integrate that in a vehicle system. Next slide. So looking at hair, that was the thing I mentioned that, these are always dramatic due to style reasons. Women are always the offenders with the longest hair. And normally they keep it tied up, but but a lot of them have actually, ponytails where it fans out quite a bit. And if you undo it all, it's quite a lot. And the question is, how big an issue is that? There's a lot of experience in the shuttle and space station that 21% is not a very big deal. But we're concerned going to higher level concentrations about what the issues were with that. Next slide, please. So we did a relatively limited study, but in using drop tower work, and we really need to extend this further. But actually, the results were dramatic. This is oxygen concentration, so this is 21%, this is 30%, and this is flame spread rate. And the important thing about this graph is it's logarithmic. And so, it goes up by virtually an order of magnitude if you go from 21% to 30%. So there's a huge increase in the flammability, both concurrent and opposed, which means whether you're blowing into the flame or with the flame. So, and even in low gravity, in those conditions, faster than 1G for one condition at 30% oxygen. So it really goes from a situation where usually when people's hair ignites, it's you've got enough time to respond and do something about it. Whereas in low gravity, really, you would not have enough time to respond and put out a fire. So it's really actually a frightening concern. And that was one thing that was actually completely unstudied, and we really need to pay more attention to it as we talk seriously about going to long-term space travel in these conditions. So in conclusion, there's a whole lot of areas of interesting research. There's been a lot of research to date that's really benefiting pollution control and increased combustion efficiency in systems such as jet engines. And we're now producing substantial results that are applicable to spacecraft fire safety conditions. Any questions?
Seems like some of the earlier slides you showed, it seems to indicate that our test one in NASA Standard 6001 seems to be not conservative. Is that your opinion? Because that's shuttle station and Orion and Constellation design is based on test one.
Well, we're not sure. The test one the conservatism is unknown, I guess, is the big concern. I think it's a good selection system for ruling out more flammable materials, but it doesn't give you much flexibility as far as, because it's just currently still a go, no-go test. So you don't know how close you are to the boundary. So it doesn't give you as much flexibility in applying materials as you want. I think that's why we'd like to extend.
But we have a way of establishing what is called a flammability threshold for every material. That is a more extensive testing. And you can find the flammability threshold of every material.
For a given geometry, you can do it. And we're working on systems that are better founded in the combustion physics in that test, which we'd like to develop more completely. But right now, it's a reasonable choice, but we'd like to get a better system that will give you better applicability. But right now, I think we're okay.
And the other thing that scared me a little bit when you said about the copper alloys, because all our high-pressure oxygen systems are, as you know, made of Monel.
Yeah.
And so if these are true safety risks, I mean, I think, you know, your team needs to work with the design standard team, and I'm part of that. So
those results were developed by the White Sands group as far as the copper, so they're very aware of it. The reality is the solution is make it thicker, and so they just. But that's. It turns out you don't have the wonderful security you have with copper-bearing alloys in 1G. But any other questions? Okay, thank you.